On August 12, 2000, a nuclear-powered submarine operated according to every specification in its technical manual. Its reactor compartments maintained designed pressure differentials. Safety systems functioned as engineered. Crew protocols followed established naval doctrine. The vessel represented the culmination of decades of submarine design philosophy, built around assumptions of operational redundancy and compartmentalized safety systems. Yet within those same design parameters lay the conditions that would make failure not just possible, but structurally inevitable. The submarine's information architecture was constructed to report system status through indicators that measured specific physical parameters while remaining silent about others. Safety protocols prioritized certain hazard categories while creating blind spots for failure modes that existed outside doctrinal expectations. The Kursk submarine embodied the intersection of three fundamental design philosophies that would prove incompatible under catastrophic stress conditions. The first was the double-hull compartmentalization doctrine, which assumed that physical isolation of systems would provide both survivability and adequate diagnostic transparency. The second was the nuclear reactor protection paradigm, which prioritized reactor safety over comprehensive damage assessment. The third was the operational security framework, which embedded information restrictions directly into emergency response protocols. The double-hull design concept represented Soviet naval engineering's response to the challenge of creating survivable attack platforms capable of engaging superior Western naval forces. According to the Norwegian Radiation Protection Authority's technical analysis, the Kursk's construction featured an outer hydrodynamic hull made of 8 mm steel plates covered with up to 80 mm of sound-dampening rubber, separated from an inner pressure hull of 50 mm. Steel by a distance varying between 1 and 2 meters. This configuration was designed around the assumption that catastrophic damage could be contained within individual compartments, allowing the submarine to maintain operational capability even after sustaining significant battle damage. The compartmentalization philosophy extended beyond physical structure into information architecture. The submarine's 9 watertight compartments were designed to function as independent operational units, each with its own life support systems, damage control equipment, and communication pathways. Emergency procedures assumed that compartment isolation would limit both physical damage and information requirements to manageable scope. This design premise created a systematic bias toward localized problem-solving that would prove inadequate when confronted, with damage patterns that exceeded compartment boundaries. The reactor protection doctrine reflected decades of Soviet nuclear engineering philosophy that placed reactor safety above all other operational considerations. The Kursk's 2 pressurized water reactors, each generating 190 megawatts of thermal power, were equipped with automatic shutdown systems designed to prioritize reactor protection over diagnostic capability. These systems functioned exactly as designed during the incident, automatically shutting down both reactors immediately upon detecting unusual conditions. However, the shutdown procedures simultaneously eliminated critical sources of diagnostic information that could have provided emergency responders with accurate assessment of the submarine's actual condition. The CIA intelligence assessment reveals that Russian naval doctrine assumed reactor shutdown would provide sufficient safety margin for extended rescue operations. This assumption embedded a fundamental contradiction into emergency response planning. The very systems designed to ensure reactor safety also rendered the submarine's actual condition opaque to both internal crew assessment and external rescue coordination. The automatic reactor protection systems functioned correctly according to their design specifications, but their operation eliminated the power generation and circulation systems that provided essential diagnostic information about compartment flooding, atmospheric conditions, and structural integrity. The operational security framework created the third layer of design assumptions that would prove problematic during crisis conditions. Soviet naval construction philosophy embedded security considerations directly into submarine design, creating information pathways that prioritized operational secrecy over emergency transparency. The Kursk's communication systems were designed around the assumption that submarine operations must maintain electronic silence to avoid detection, with emergency communication protocols that assumed rescue operations would be conducted entirely within Russian naval capabilities. The emergency buoy system exemplified this security-first design philosophy. According to technical specifications, an ascending buoy located on compartment 7 should have automatically released upon detecting emergency conditions, providing surface notification and communication capability. The Harvard Business School analysis indicates this system failed to activate during the incident, not due to mechanical failure but because its automatic release criteria were calibrated around operational security requirements rather than pure emergency detection. The system was designed to avoid compromising submarine location data except under conditions that met specific classification criteria. These three design philosophies created systematic vulnerabilities that were not apparent under normal operational conditions but became critical during the specific failure mode that occurred. The compartmentalization doctrine assumed that catastrophic damage could be contained within design parameters, but the explosive event that initiated the crisis exceeded these assumptions by several orders of magnitude. Norwegian seismic data recorded two explosions, the first measuring 1.5 on the Richter scale, and the second measuring 3.5, indicating energy release levels that far exceeded the containment capabilities of individual compartment boundaries. The reactor protection doctrine assumed that reactor shutdown would provide adequate safety margins for rescue operations while maintaining sufficient system capability for damage assessment. However, the automatic shutdown procedures eliminated critical information pathways precisely when comprehensive system assessment became most crucial. The CIA analysis confirms that Russian rescue coordinators operated with incomplete understanding of the submarine's actual condition, because the reactor shutdown protocols, while successful in preventing nuclear hazards, also eliminated diagnostic capabilities needed for effective rescue planning. The operational security framework assumed that rescue operations would be conducted within established Russian naval capabilities, with international assistance limited to predetermined coordination protocols. The Harvard analysis documents how these assumptions created systematic delays in international rescue coordination, as security protocols required extensive approval processes that consumed critical time, while survivors remained trapped in deteriorating conditions. The interaction between these three design philosophies created emergent failure modes that were not anticipated by individual system designs. The compartmentalization doctrine's assumption of localized damage control proved inadequate when explosive forces exceeded compartment boundaries, creating flooding patterns that overwhelmed individual compartment isolation capabilities. The reactor protection doctrine's prioritization of nuclear safety over diagnostic capability left rescue coordinators operating with limited understanding of survivability conditions within the submarine. The operational security framework's emphasis on maintaining classified information control created communication barriers that prevented effective coordination between Russian capabilities and available international rescue assets. The submarine's instrumentation architecture reflected these embedded assumptions in its sensor placement, data processing priorities, and information distribution pathways. Critical diagnostic sensors were positioned to monitor normal operational parameters and anticipated failure modes within design specifications. However, the explosive damage created sensor failure patterns that fell outside diagnostic system assumptions, rendering much of the available instrumentation ineffective for assessing actual post-incident conditions. The emergency response procedures, embedded within crew training protocols, reflected similar assumptions about damage patterns and rescue timeframes. According to the Norwegian analysis, crew members were distributed across compartments according to normal operational assignments, with emergency procedures that assumed localized damage scenarios allowing for systematic evacuation through established escape routes. The actual damage pattern rendered these procedures inadequate, as the forward compartments containing primary escape systems were destroyed immediately, leaving survivors trapped in AFT compartments with limited emergency equipment designed for temporary survival, rather than extended rescue operations. The training doctrine prioritized reactor-related emergency procedures over comprehensive damage assessment, reflecting institutional assumptions about primary threat categories. Crew members were extensively trained in reactor emergency protocols, but received limited training in complex damage assessment scenarios that might require coordination between multiple emergency systems. This training bias proved problematic when the actual emergency required comprehensive assessment of structural damage, flooding patterns, and atmospheric conditions across multiple compromised compartments. The International Rescue Coordination Framework reflected institutional assumptions about operational sovereignty and technical capability sharing that proved incompatible with the specific requirements of the emergency. Russian naval doctrine assumed that submarine rescue operations could be conducted using domestic capabilities, with international assistance limited to predetermined technical support functions. The Harvard analysis reveals that these assumptions created systematic barriers to effective international coordination, as existing protocols were not designed to accommodate the rapid integration of foreign technical capabilities under time-critical conditions. The institutional decision-making framework embedded assumptions about information requirements, authorization hierarchies, and technical risk assessment that proved inadequate when confronted with the specific combination of technical unknowns and time pressure created by the incident. The CIA assessment documents how institutional protocols designed for normal operational security conflicted with emergency response requirements for rapid information sharing and decision-making authority delegation. These design assumptions, individually rational within their respective domains, created systematic incompatibilities when combined under crisis conditions. The compartmentalization philosophy's emphasis on isolation conflicted with the information sharing requirements of effective rescue coordination. The reactor protection doctrine's prioritization of nuclear safety conflicted with the diagnostic transparency needed for rescue planning. The operational security framework's emphasis on information control conflicted with the coordination requirements of international rescue operations. The forensic examination reveals that the disaster resulted not from single-point failures within individual systems, but from the emergent properties of design philosophies that functioned according to specification while creating conditions for systematic failure. Each design assumption proved logical within its intended operational context, but the interaction between these assumptions under catastrophic stress conditions created emergent vulnerabilities that were not anticipated by individual system designers. The emergency surfacing and communication protocols embedded within Northern Fleet operational doctrine reflected institutional priorities that created systematic vulnerabilities in crisis response capability. These protocols, developed through decades of operational experience and refined according to established naval tradition, functioned effectively under anticipated emergency scenarios, but proved inadequate when confronted with the specific combination of technical failures and time constraints that characterized the incident. The training doctrine emphasized reactor protection procedures over comprehensive damage assessment, reflecting institutional assumptions about primary threat categories during submarine emergencies. According to the Norwegian Radiation Protection Authority's analysis, crew members received extensive training in reactor emergency protocols but limited preparation for complex structural damage scenarios requiring coordination between multiple emergency systems. This training bias created cognitive patterns that prioritized reactor safety over situational awareness precisely when comprehensive system assessment became most critical for survival. The crew distribution during submerged operations reflected standard operational doctrine that assumed normal emergency response capabilities. The Norwegian analysis documents that personnel were stationed with 7 members in the forward torpedo compartment, 36 in the control room, 24 in the combat station and radio room, 12 in living quarters, 15 in various operational stations, 5 in the reactor compartment, 9 in the main propulsion compartment, 7 in the secondary propulsion area, and 3 in the aft electrical motor section. This distribution pattern optimized normal operational efficiency but concentrated critical emergency response expertise in forward compartments that would be destroyed immediately during the initiating event. The communication hierarchy embedded within Northern Fleet protocols created systematic delays in critical information transmission during crisis conditions. The CIA intelligence assessment reveals that initial emergency notification followed established chain-of-command protocols that prioritized operational security over rapid information dissemination. Admiral Vyacheslav Popov, Commander-in-Chief of the Northern Fleet, issued emergency alarm procedures at 23:30 on August 12, approximately 5.5 hours after the explosions occurred. This delay reflected standard operational protocols that required verification of emergency conditions through established communication channels before activating fleet-wide emergency response procedures. The duty officer procedures embedded additional verification requirements that consumed critical time while survivors remained trapped in deteriorating conditions. According to the CIA analysis, the Navy's Moscow Command Center contacted Rear Admiral Gennady Verich, head of Russian Navy Search and Rescue Forces, at 5 on August 13, approximately 10 hours after the initial explosions. Verich's first response followed established institutional protocol, gathering staff officers and planning response procedures, rather than immediately deploying available rescue assets. These protocols reflected institutional assumptions about emergency verification requirements that proved incompatible with the time-critical nature of submarine rescue operations. The interface design prioritized normal operational efficiency over emergency diagnostic capability, creating systematic barriers to accurate damage assessment under crisis conditions. The submarine's control systems were optimized for trained operators working under normal operational parameters, with emergency interfaces that assumed crew familiarity with standard diagnostic procedures. However, the explosive damage created system states that fell outside normal operational parameters, rendering much of the available diagnostic capability ineffective for assessing actual post-incident conditions. The emergency communication systems reflected design assumptions about rescue coordination that proved inadequate when confronted, with the specific combination of damage patterns and operational constraints. The automatic emergency buoy system, designed to provide surface notification and communication capability, failed to activate because its release criteria were calibrated around operational security requirements rather than pure emergency detection. The Norwegian analysis indicates that this system was designed to avoid compromising submarine location data except under conditions that met specific classification criteria, creating systematic bias against automatic emergency notification. The procedural gaps between submarine emergency protocols and surface rescue capabilities reflected institutional assumptions about rescue timeframes and coordination requirements that proved optimistic under actual conditions. Russian naval doctrine assumed that submarine rescue operations could be conducted using domestic capabilities within timeframes compatible with submarine crew survival requirements. However, the Harvard Business School analysis reveals that available Russian rescue systems were designed around different emergency scenarios and technical specifications than those created by the incident. The rescue submersible coordination procedures assumed compatibility between submarine emergency systems and surface rescue equipment that did not exist under actual damage conditions. According to the Norwegian analysis, Russian rescue attempts during the first week involved 22 vessels and 3,000 personnel, but these assets were designed for different damage scenarios than those created by the explosive event. The rescue submersibles could not establish effective connection with the damaged emergency escape systems because the explosion had compromised the docking platforms and surrounding hull sections beyond the design assumptions of rescue equipment interfaces. The maintenance practices reflected resource constraints that affected emergency response equipment readiness under budget-limited operations. The CIA assessment documents that by 2000, the condition of Russian naval support infrastructure had deteriorated significantly due to repeated budget cuts. Submarine rescue equipment, torpedo loading systems, and training facilities had not received adequate maintenance funding, creating systematic degradation in emergency response capability. In 1995, the Northern Fleet's annual budget was exhausted in the first half of the year, resulting in suspended salary payments and deferred maintenance activities. The crew training emphasis reflected institutional priorities that created cognitive biases toward reactor-centric threat assessment rather than comprehensive emergency evaluation. Submarine personnel received extensive preparation in nuclear safety protocols, but limited training in damage assessment scenarios that might require rapid decision-making about escape route selection, emergency equipment deployment, and coordination with surface rescue assets. This training pattern reflected institutional assumptions about primary threat categories that proved inadequate when confronted with structural damage that eliminated primary emergency response systems. The communication system design embedded operational security requirements that conflicted with emergency coordination needs. The submarine's communication equipment was designed to maintain electronic silence during normal operations, with emergency communication protocols that assumed rescue coordination would occur within established Russian naval command structures. However, the Harvard analysis reveals that effective rescue operations required rapid information sharing between Russian assets and available international rescue capabilities, creating systematic conflict between operational security protocols and emergency response requirements. The emergency equipment distribution reflected design assumptions about crew survival scenarios that proved inadequate under actual incident conditions. Emergency life support systems were designed around assumptions about damage patterns that would allow crew members to reach designated emergency stations with adequate equipment for temporary survival. However, the explosive event created damage patterns that isolated survivors in compartments with limited emergency equipment designed for short-term survival rather than extended rescue operations. The 23 crew members who survived the initial explosions found themselves trapped in the 9th compartment with emergency equipment calibrated for rescue timeframes significantly shorter than those actually required. The institutional decision-making framework embedded authorization hierarchies that created systematic delays in emergency response coordination. The CIA analysis documents how senior Russian officials maintained operational security protocols that prevented rapid coordination with available international rescue assets. Norwegian Admiral Einar Skorgan offered assistance through direct military-to-military communication channels on August 14, but was informed that the situation is under control and we have no need for any assistance. This response reflected institutional protocols that prioritized operational autonomy over external rescue coordination, creating systematic barriers to effective resource utilization. The interface between Russian naval protocols and international rescue capabilities reflected institutional assumptions about sovereignty and technical coordination that proved incompatible with emergency response requirements. The Harvard analysis reveals that available rescue systems from British and Norwegian sources possessed technical capabilities that could potentially have assisted rescue operations, but existing coordination protocols were not designed to accommodate rapid integration of foreign technical assets under time-critical conditions. The institutional framework assumed that international assistance would be provided through predetermined coordination channels with extensive verification and approval procedures. The budget constraints created systematic degradation in emergency response equipment and training that became critical during actual emergency conditions. The Norwegian analysis documents that Russian naval capabilities had been significantly reduced due to resource limitations, with the defense budget allocation to naval operations declining from 23% in 1993 to 9.2% in 1998. This resource constraint affected maintenance of emergency response equipment, crew training frequency, and availability of specialized rescue assets precisely when comprehensive emergency response capability became most crucial. The crew interface design reflected assumptions about emergency response coordination that assumed availability of primary communication and navigation systems. Emergency procedures were designed around scenarios where crew members could maintain communication between compartments and coordinate emergency response activities through established command structures. However, the explosive damage eliminated primary communication pathways between compartments, leaving survivors isolated without effective coordination capability. Captain Lieutenant Dmitry Kolesnikov assumed command of survivors in the 9th compartment, but operated without communication links to other potential survivor groups or surface rescue coordination. The training doctrine created systematic cognitive patterns that emphasized adherence to established protocols over adaptive problem-solving under novel emergency conditions. Crew members were extensively trained in specific emergency procedures, but received limited preparation for scenarios requiring improvisation or deviation from standard protocols. This training pattern reflected institutional assumptions about emergency response that prioritized procedural compliance over situational adaptation, creating potential barriers to effective response under conditions that exceeded standard emergency scenarios. The emergency response equipment reflected design assumptions about rescue coordination timeframes that proved optimistic under actual conditions. Life support systems were calibrated for survival periods that assumed rapid rescue response, using available Russian naval assets. However, the actual rescue coordination required significantly longer timeframes due to equipment compatibility problems, authorization delays, and technical challenges that exceeded design assumptions. The emergency equipment provided adequate life support for anticipated rescue timeframes, but proved insufficient for the extended periods required by actual rescue coordination. The institutional communication framework created systematic barriers between operational security requirements and emergency information sharing needs. Russian naval protocols emphasized maintaining classified information control even during emergency conditions, creating systematic delays in providing technical information needed for effective rescue coordination. International rescue assets required detailed technical specifications about submarine design, emergency system configuration, and damage assessment to deploy effective rescue capability, but institutional protocols prevented rapid information sharing that could have expedited rescue operations. The forward torpedo compartment explosion sequence created damage patterns that exceeded every design parameter for contained emergency response. Yet the submarine's automatic safety systems functioned exactly according to their specifications, generating system responses that crew members interpreted through established training frameworks that no longer corresponded to physical reality. This divergence between actual system conditions and perceived system state represented the critical transition point where normal operational procedures became not merely inadequate, but systematically misleading. Norwegian seismic monitoring stations recorded the initiating sequence as two distinct events occurring within minutes of each other on the morning of August 12, 2000. The first explosion registered 1.5 on the Richter scale at 7:29:50 GMT, followed by a significantly larger detonation measuring 3.5 on the Richter scale at 7:32 GMT. The Norwegian Radiation Protection Authority's analysis indicates that this energy release pattern was consistent with an initial torpedo malfunction, followed by sympathetic detonation of additional warheads stored within the forward torpedo compartment, creating explosive forces several orders of magnitude beyond the containment capabilities designed into individual compartment boundaries. The submarine's automatic reactor protection systems detected the explosive shock waves and initiated emergency shutdown procedures exactly as programmed, prioritizing nuclear safety over all other operational considerations. Both pressurized water reactors, each generating 190 megawatts of thermal power, were automatically isolated from primary cooling circulation, and control rod insertion achieved full reactor shutdown within seconds of the initial explosion detection. These procedures functioned flawlessly according to their design specifications, eliminating immediate nuclear hazards but simultaneously removing critical power generation that provided essential information about overall system status. The reactor shutdown eliminated primary electrical generation that powered critical diagnostic instrumentation throughout the submarine's monitoring systems. Emergency battery systems activated according to design specifications, providing power for essential life support and emergency lighting. But the reduced electrical capacity limited diagnostic capability, precisely when comprehensive damage assessment became most crucial for crew survival decisions. The automatic safety systems functioned correctly within their programmed parameters, but their operation created information gaps that rendered accurate damage assessment nearly impossible. The explosion propagated through the submarine's structure in patterns that violated fundamental assumptions embedded within damage control doctrine. The double-hull design was intended to contain catastrophic damage within individual compartments, but the explosive forces exceeded the structural limits of compartment boundaries, creating progressive failure that compromised multiple, watertight sections simultaneously. The Norwegian analysis indicates that the explosion destroyed the first 5 compartments instantly, eliminating not only the crew members stationed in these areas but also the primary emergency escape systems and damage control equipment designed to respond to contained emergency scenarios. The emergency communication systems reflected this divergence between design assumptions and actual damage patterns. The automatic emergency buoy system failed to activate, not due to mechanical malfunction, but because the explosive damage exceeded the system's programmed activation criteria. The buoy release mechanism was calibrated to respond to specific combinations of depth, pressure, and electrical system status that would indicate controlled emergency conditions, but the explosive damage created system states that fell outside these program parameters. The safety system functioned according to its design logic, while failing to provide emergency notification capability when it became most critically needed. The crew members who survived the initial explosions found themselves operating within a system environment that appeared familiar through their training experience but represented fundamentally different physical conditions than any emergency scenario addressed by established procedures. The 23 survivors gathered in the 9th compartment retained access to emergency life support systems that functioned normally, creating the impression that standard emergency procedures remained applicable to their situation. However, the elimination of forward compartments had destroyed primary escape routes and emergency equipment that formed the foundation of established emergency response protocols. Captain Lieutenant Dmitry Kolesnikov's initial response demonstrated the systematic nature of this perception gap between trained procedures and actual conditions. According to the Harvard Business School analysis, Kolesnikov followed standard emergency protocols by conducting crew accountability procedures and establishing emergency communications within the survivor group. At 13:34 on August 12, approximately 6 hours after the explosions, he documented survivor names and ranks using standard emergency reporting procedures. These actions reflected appropriate adherence to training doctrine, but the procedures were designed around assumptions about communication capability and rescue coordination that no longer existed due to the explosive damage. The atmospheric monitoring systems within the 9th compartment provided readings that reinforced the impression that standard emergency procedures remained applicable. Life support systems continued to function normally, maintaining breathable atmosphere and acceptable temperature conditions that suggested adequate time remained for systematic rescue coordination. However, these readings reflected only local conditions within the isolated compartment and provided no information about overall submarine status, rescue coordination progress, or external emergency response activities that would determine actual survival prospects. The emergency escape systems exhibited similar divergence between apparent functionality and actual capability. The escape tower within the 9th compartment appeared to function normally, with mechanical systems and pressure equalization procedures operating according to design specifications. Crew members could observe that emergency equipment remained accessible and escape procedures could theoretically be initiated. However, the explosive damage had compromised external systems needed to complete emergency ascent procedures, creating systematic disconnect between apparent escape capability and actual rescue prospects. The communication equipment within the survivor compartment maintained local functionality while providing no indication of the comprehensive communication system failures created by explosive damage. Emergency communication devices operated normally within the compartment, suggesting that standard emergency notification procedures could be initiated when rescue assets became available. However, the destruction of primary communication pathways prevented transmission of emergency information to surface rescue coordination, creating critical gap between crew expectations and actual rescue coordination capability. The flooding patterns reflected similar systematic deviation from design assumptions embedded within emergency response procedures. The compartmentalization doctrine assumed that flooding could be controlled through established damage control procedures using equipment and expertise distributed throughout the submarine's compartments. However, the explosive damage eliminated both the equipment and personnel needed for damage control activities, while creating flooding rates that exceeded the capacity of surviving emergency systems. Water ingress occurred through multiple breach points created by explosive forces, generating flooding patterns that could not be controlled through procedures designed for contained damage scenarios. The reactor protection systems continued to provide status information that reflected successful nuclear safety maintenance while providing no indication of overall system degradation that affected rescue prospects. Automatic monitoring systems confirmed that reactor shutdown had been achieved and that nuclear safety systems remained functional, creating the impression that primary emergency objectives had been met. However, this information addressed only nuclear safety considerations and provided no assessment of structural integrity, flooding progression, or emergency escape system capability that determined actual survival requirements. The emergency power systems demonstrated additional aspects of this systematic divergence between system functionality and rescue capability. Battery systems activated according to design specifications and maintained power for essential life support systems, suggesting that adequate resources remained for extended emergency operations. Emergency lighting continued to function normally, life support circulation maintained acceptable atmospheric conditions, and emergency communication equipment remained operational within the compartment. These indicators suggested that standard emergency procedures could be sustained for the time frames assumed by rescue coordination protocols. However, the battery systems were designed to provide emergency power for rescue scenarios that assumed availability of primary emergency response systems eliminated by the explosive damage. The emergency power could sustain life support systems within the isolated compartment for predetermined timeframes, but provided no capability for external communication, emergency ascent procedures, or coordination with surface rescue assets. The power systems functioned correctly according to their design specifications while being unable to support actual rescue requirements created by the comprehensive system damage. The pressure equalization systems within the escape tower reflected similar functional capability that could not address actual emergency requirements. Emergency procedures for escape tower utilization assumed availability of surface rescue coordination that could provide external support for emergency ascent activities. The pressure systems could theoretically support emergency escape procedures, but the destruction of communication systems eliminated coordination capability needed to ensure surface rescue assets would be positioned appropriately to assist emergency ascent operations. The crew members interpreted these apparently functional systems through training frameworks that assumed rescue coordination would proceed according to established protocols. Standard emergency procedures emphasized maintaining life support systems, conducting systematic damage assessment, and preparing for rescue coordination activities that would be initiated through normal command structure channels. These procedures remained logically applicable to the apparent system conditions within the survivor compartment. But the explosive damage had eliminated the external coordination capabilities that made these procedures effective for actual rescue operations. The systematic nature of this divergence between apparent system capability and actual rescue requirements created decision-making conditions that were inherently misleading. Every system indicator that remained functional suggested that standard emergency procedures could be sustained and that rescue coordination would proceed according to established protocols. However, the explosive damage had eliminated critical external systems needed to make these procedures effective, creating systematic disconnect between crew assessment and actual survival prospects that could not be resolved through additional system monitoring or procedural compliance. The compartment flooding patterns following the explosive breach followed predictable fluid dynamics principles, but the rate and distribution of water ingress exceeded every design assumption embedded within emergency response protocols and life support system capacity. The physical processes governing flood progression operated according to fundamental engineering principles, while creating conditions that evolved beyond the capability of emergency equipment to maintain survivable atmospheric conditions within the timeframes required for rescue coordination. The explosive damage created multiple breach points in the submarine's pressure hull that allowed seawater ingress at rates determined by hydrostatic pressure differentials and available flow areas. At the incident depth of 116 meters, external water pressure reached approximately 12.6 atmospheres, creating driving forces for flood progression that exceeded the capacity of emergency pumping systems designed for controlled leakage scenarios. The Norwegian Radiation Protection Authority's analysis indicates that the submarine's emergency dewatering capability was calibrated for drainage rates compatible with contained damage patterns, not catastrophic hull breach scenarios that created unrestricted flow pathways. The compartmentalization doctrine assumed that watertight bulkheads would limit flooding to specific areas while maintaining emergency response capability in undamaged sections. However, the explosive forces compromised bulkhead integrity across multiple compartments simultaneously, creating progressive flooding patterns that exceeded the isolation capability of individual watertight barriers. The destruction of the first 5 compartments eliminated not only physical barriers to flood progression, but also the emergency equipment and trained personnel needed to implement damage control procedures designed for contained flooding scenarios. The atmospheric control systems within the surviving AFT compartments continued to function according to their design specifications, while operating under conditions that fundamentally altered their effectiveness for maintaining long-term habitability. The emergency life support systems were designed to maintain breathable atmosphere for predetermined survival periods, assuming availability of rescue assets within established response timeframes. However, the elimination of primary communication and escape systems extended required survival duration beyond the design capacity of atmospheric control equipment. The oxygen generation and carbon dioxide removal systems within Compartment 9 maintained local atmospheric quality during initial survival periods, creating conditions that reinforced crew assessment that standard emergency procedures remained applicable. Emergency atmosphere monitoring indicated acceptable oxygen levels and carbon dioxide concentrations that suggested adequate life support capability for anticipated rescue operations. However, these systems operated with limited consumable supplies designed for emergency scenarios of significantly shorter duration than those created by the comprehensive rescue coordination delays. The pressure equalization systems demonstrated the systematic nature of physical constraints that rendered emergency escape procedures theoretically possible but practically infeasible under actual damage conditions. The escape tower within Compartment 9 could maintain pressure differential management needed for emergency ascent operations, but the explosive damage had compromised external hull integrity around the escape system interfaces. Emergency ascent procedures assumed structural continuity between internal escape systems and external hull configuration that no longer existed due to explosive deformation of surrounding hull sections. The thermal environment within the survivor compartment reflected heat transfer characteristics that initially supported crew survival, but created progressive degradation in environmental conditions over extended periods. Emergency heating systems maintained acceptable temperature conditions during immediate post-incident periods, but the elimination of primary power generation reduced heating capability, while hull breach areas created thermal conduction pathways that gradually degraded internal temperature maintenance. The combination of reduced heating capacity and increased thermal losses created environmental conditions that progressively compromised crew endurance capability. The atmospheric contamination patterns reflected chemical processes initiated by explosive damage to systems containing hazardous materials distributed throughout the submarine's operational areas. The destruction of battery compartments released electrolyte vapors, damaged electrical systems generated toxic combustion products, and compromised hydraulic systems leaked fluids that created atmospheric contamination when volatilized by thermal conditions. Emergency atmospheric monitoring systems detected these contaminants but provided limited capability for atmospheric purification beyond design specifications for normal operational air quality maintenance. The emergency equipment consumption rates reflected usage patterns that exceeded design assumptions about rescue coordination timeframes and crew survival requirements. Emergency oxygen supplies, battery power, food rations, and fresh water were calibrated for survival periods compatible with anticipated Russian naval rescue response capability. However, the actual rescue coordination required significantly longer timeframes due to equipment compatibility problems, authorization delays, and technical challenges that exceeded design assumptions embedded within emergency supply calculations. The carbon dioxide accumulation patterns demonstrated fundamental atmospheric chemistry constraints that became critical factors in crew survival capability over extended periods. Emergency CO2 removal systems could maintain acceptable atmospheric conditions for predetermined timeframes, but the chemical absorption media had limited capacity that could not be replenished under actual survival conditions. As CO2 levels gradually increased beyond acceptable limits, crew members experienced physiological effects that compromised decision-making capability and physical endurance needed for potential emergency escape operations. The whole structural integrity around escape system interfaces reflected mechanical damage patterns that created systematic barriers to emergency ascent procedures despite apparent functionality of internal escape equipment. The escape tower pressure systems could theoretically support emergency ascent operations, but explosive deformation had compromised external hull areas needed to complete ascent procedures safely. Emergency escape required coordination between internal pressure management and external hull configuration that could no longer be achieved due to structural damage patterns created by explosive forces. The flooding progression through interconnected compartment areas followed hydrodynamic principles that created systematic advancement of water ingress beyond the capacity of emergency pumping systems to maintain habitability. Water entered through multiple breach points and flowed through compromised bulkhead penetrations according to pressure differential and gravitational forces, creating flood patterns that progressively eliminated habitable volume within the submarine. Emergency pumping systems functioned according to their design specifications, but possessed insufficient capacity to offset flooding rates determined by unrestricted hull breach areas. The emergency lighting systems demonstrated progressive degradation in capability as battery power was consumed for life support systems that required extended operation beyond design assumptions. Emergency illumination remained functional during initial survival periods, providing adequate visibility for crew coordination and emergency equipment operation. However, power consumption for life support systems created systematic reduction in lighting capability that gradually compromised crew effectiveness for potential emergency response activities while conserving battery capacity for essential atmospheric control functions. The chemical processes within emergency life support systems created byproducts that accumulated over time and contributed to atmospheric quality degradation beyond the capacity of emergency purification equipment. Oxygen generation systems produced hydrogen as a byproduct that required venting capability eliminated by hull damage. Carbon dioxide removal systems generated heat that contributed to thermal load beyond emergency cooling capacity. And emergency power systems created combustion products that accumulated in atmospheric circulation systems designed for shorter operational periods. The pressure management systems within the escape tower reflected fundamental physics constraints that prevented emergency ascent operations despite apparent equipment functionality. Emergency escape procedures required precise pressure differential management between internal escape chamber and external water pressure to prevent physiological damage during rapid ascent. However, the explosive damage had created hull breach patterns around escape system interfaces that eliminated pressure isolation capability needed to implement emergency ascent procedures safely. The emergency communication equipment within the survivor compartment maintained local operational capability while being unable to establish external communication pathways needed for rescue coordination. Emergency transmitters functioned according to design specifications and could theoretically initiate communication with surface rescue assets, but the destruction of antenna systems and communication infrastructure eliminated transmission capability. Crew members could operate communication equipment normally, but could not establish contact with rescue coordination activities occurring above the incident site. The atmospheric pressure management within the flooded compartments created systematic changes in gas composition that affected crew physiology over extended survival periods. As compartment flooding progressed, atmospheric pressure increased due to compression of remaining air spaces, creating conditions similar to deep diving scenarios that required gradual decompression procedures for safe emergency escape. However, emergency escape equipment was not designed for extended high-pressure exposure scenarios. creating additional physiological constraints on potential rescue operations. The emergency food and water supplies reflected consumption calculations based on crew survival requirements for anticipated rescue timeframes that proved insufficient for actual rescue coordination duration. Emergency rations could sustain crew metabolism for predetermined periods, assuming rescue operations would proceed according to established protocols. But actual rescue coordination required significantly longer survival periods due to equipment compatibility problems and authorization delays. Progressive depletion of emergency supplies created physiological stress that compromised crew endurance capability during critical survival periods. The thermal transfer characteristics through compromised hull areas created progressive heat loss that exceeded emergency heating system capacity over extended periods. Hull breach areas provided thermal conduction pathways to external seawater temperature that gradually overwhelmed internal heating capability, creating environmental conditions that required increased metabolic energy expenditure for thermal regulation. Emergency heating systems functioned according to design specifications but could not maintain acceptable thermal conditions when operating against thermal loads created by extensive hull damage. The atmospheric circulation patterns within the survivor compartment reflected fluid dynamics constraints that gradually reduced air quality despite continued operation of emergency ventilation systems. Emergency ventilation could maintain atmospheric circulation for predetermined periods, but the elimination of external ventilation pathways created recirculation patterns that gradually concentrated atmospheric contaminants beyond the capacity of emergency purification systems. Air quality degraded progressively despite normal operation of emergency ventilation equipment designed for scenarios with external atmospheric exchange capability. The Northern Fleet rescue capabilities reflected institutional assumptions about emergency response scenarios that proved systematically incompatible with the technical requirements and coordination complexity created by the incident. Russian naval rescue doctrine, developed through decades of operational experience with submarine emergencies, assumed that domestic rescue assets could provide adequate response capability within timeframes compatible with crew survival requirements, but the actual technical challenges exceeded both equipment specifications and coordination protocols embedded within established rescue procedures. Admiral Vyacheslav Popov's initial rescue coordination efforts followed standard Northern Fleet protocols that emphasized rapid deployment of available Russian assets, while maintaining operational security constraints around submarine technical information. The CIA intelligence assessment documents that 22 vessels and 3,000 personnel were deployed during the first week of rescue operations, representing the largest Russian naval rescue coordination since the collapse of the Soviet Union. However, these assets were designed for different emergency scenarios than those created by the explosive damage pattern, creating systematic mismatches between available rescue capability and actual technical requirements. The rescue submersible systems available within Russian naval inventory were calibrated for emergency scenarios that assumed functional submarine emergency interfaces and communication capability. The primary rescue vehicle attempted to establish docking connection with the submarine's aft escape hatch using procedures designed for submarines with operational emergency systems, but the explosive damage had compromised the docking ring structure and surrounding hull integrity beyond the compatibility range of rescue equipment interfaces. Multiple rescue attempts between August 13 and August 17 failed to achieve effective docking seal because rescue submersible specifications assumed emergency interface conditions that no longer existed due to explosive deformation. The Norwegian diplomatic intervention through direct military communication channels revealed systematic barriers embedded within Russian institutional protocols that prioritized operational security over international rescue coordination. Admiral Einar Skorgan contacted Admiral Popov on August 14 through established military-to-military communication channels, offering Norwegian assistance in rescue operations, but received response indicating that the situation is under control and we have no need for any assistance. This response reflected institutional protocols designed to maintain operational sovereignty during submarine emergencies, creating systematic delays in accessing international rescue capabilities that possessed different technical specifications potentially compatible with actual damage conditions. The timeline constraints imposed by crew survival requirements created systematic pressure on rescue decision making that conflicted with authorization procedures embedded within institutional coordination protocols. The Harvard Business School analysis indicates that effective rescue operations required technical information sharing and coordination authority delegation that contradicted established security protocols for submarine operations. Russian rescue coordinators operated under institutional constraints that prevented rapid information sharing needed for effective international technical cooperation, while crew survival capability deteriorated according to life support system limitations that could not be extended through procedural modifications. The British rescue system deployment reflected international coordination capabilities that possessed technical specifications potentially compatible with actual rescue requirements. But institutional barriers prevented effective integration of rescue assets within critical timeframes. The LR-5 rescue submersible was transported to Norwegian facilities and prepared for rescue operations, but Russian authorization for deployment required coordination procedures that consumed critical time, while atmospheric conditions within the survivor compartment deteriorated beyond reversible limits. The rescue system possessed technical capability for deep-water rescue operations, but could not be deployed effectively due to coordination protocol limitations. The Norwegian offshore diving capabilities represented additional rescue resources with technical specifications adapted for North Sea operations that could potentially address rescue requirements created by the specific damage patterns. According to the Norwegian Radiation Protection Authority analysis, Norwegian diving assets possessed capabilities for deep water operations, hull cutting procedures, and emergency access techniques developed for offshore oil industry applications. However, integration of these capabilities required information sharing about submarine technical specifications and damage assessment data that conflicted with operational security protocols maintained by Russian rescue coordination. The weather conditions during rescue operations created additional technical constraints that affected both Russian rescue submersibles and potential international rescue coordination. Surface conditions in the Barents Sea during mid-August included wave heights and wind patterns that compromised precision maneuvering required for rescue submersible docking operations. Russian rescue coordinators attributed multiple rescue attempt failures to weather-related operational limitations. But the CIA assessment suggests that equipment compatibility problems represented more significant barriers to effective rescue coordination than environmental conditions. The communication system limitations between surface rescue coordination and trapped crew members created systematic gaps in rescue planning information that prevented optimization of rescue procedures for actual survivor conditions. Russian rescue coordination operated without direct communication capability to assess crew status, atmospheric conditions, or emergency equipment availability within the survivor compartment. Rescue planning proceeded according to assumptions about survivor conditions and emergency capability that could not be verified through direct communication, creating systematic mismatches between rescue procedures and actual survivor requirements. The time pressure effects on institutional decision-making revealed systematic conflicts between authorization protocols designed for normal operational security and emergency response requirements for rapid technical coordination. Russian institutional protocols required authorization hierarchies for international cooperation that assumed adequate time for coordination procedure completion, but crew survival timeline constraints required decision-making authority delegation that conflicted with established security protocols. The CIA analysis documents how senior officials maintained security protocols that prevented effective international rescue coordination, even when domestic rescue capabilities proved inadequate for actual technical requirements. The rescue equipment compatibility problems reflected fundamental design differences between Russian submarine emergency systems and international rescue capabilities that prevented effective technical integration despite availability of multiple rescue assets. Russian submarine emergency interfaces were designed for compatibility with Russian rescue submersibles using specific docking procedures and pressure management protocols, while international rescue systems utilized different technical approaches that required information sharing and coordination procedures prohibited by operational security constraints. The secondary crisis development occurred when initial rescue attempts created additional technical challenges that further compromised rescue coordination effectiveness. Multiple failed docking attempts damaged remaining emergency interface components, reducing compatibility with both Russian and international rescue systems. The Norwegian analysis indicates that rescue submersible operations created additional structural stress on damaged hull areas around escape systems, potentially compromising remaining structural integrity needed for subsequent rescue attempts using different technical approaches. The institutional learning limitations became apparent when rescue coordination continued to emphasize Russian asset deployment despite evidence of systematic equipment compatibility problems that required alternative technical approaches. Russian rescue protocols assumed that sufficient rescue attempts using domestic capabilities would eventually achieve effective docking connection, but the explosive damage had created interface conditions that exceeded the adaptation capability of available rescue equipment. Continued emphasis on Russian rescue approaches consumed critical time, while alternative international rescue capabilities remained unavailable due to authorization protocol barriers. The technical information sharing constraints prevented effective damage assessment coordination that could have optimized rescue procedures for actual damage conditions, rather than assumed emergency scenarios. International rescue capabilities required detailed technical specifications about submarine design, damage patterns, and emergency system configuration to deploy effective rescue procedures, but Russian security protocols prevented information sharing needed for rescue optimization. Rescue coordination proceeded according to standard emergency assumptions rather than technical assessment of actual conditions created by explosive damage. The rescue resource allocation reflected institutional priorities that emphasized demonstrating Russian rescue capability over optimizing rescue effectiveness through international technical cooperation. The deployment of extensive Russian naval assets served institutional objectives related to operational competence demonstration, but did not address fundamental technical compatibility problems that prevented effective rescue coordination. The Harvard analysis suggests that institutional priorities related to operational sovereignty created systematic barriers to rescue optimization that could have been achieved through international technical cooperation. The authorization hierarchy limitations created systematic delays in rescue decision-making when time constraints required rapid technical coordination and deployment authority delegation. Russian institutional protocols required senior authorization for international cooperation and technical information sharing, but rescue effectiveness required real-time technical coordination between rescue assets and surface support operations. Authorization delays consumed critical time, while crew survival capability deteriorated according to life support system limitations that could not be extended through procedural compliance. The operational security maintenance during emergency conditions created systematic conflicts between information control requirements and technical coordination needs for effective rescue operations. Russian protocols emphasized maintaining submarine technical information security even during rescue operations, preventing international rescue coordination that required technical specification sharing for equipment compatibility assessment. Security protocol maintenance served institutional objectives, but created barriers to rescue effectiveness that proved insurmountable within crew survival timeline constraints. The rescue coordination complexity increased as multiple international rescue capabilities became available but could not be effectively integrated due to institutional protocol barriers that prevented rapid technical coordination. British, Norwegian, and Russian rescue assets possessed complementary technical capabilities that could potentially have addressed rescue requirements through coordinated deployment, but institutional barriers prevented effective integration within timeframes compatible with crew survival requirements. Rescue coordination became increasingly complex as additional resources became available without corresponding improvements in coordination effectiveness. The post-incident metallurgical analysis of recovered components provided definitive physical evidence that confirmed the engineering analysis of damage progression and validated the timeline of crew survival that had been inferred from system behavior patterns during rescue operations. The physical evidence revealed how explosive forces had exceeded design assumptions by measurable margins and documented the systematic nature of institutional responses that had prioritized information control over rescue optimization, leading to comprehensive modifications in submarine safety doctrine and international emergency cooperation frameworks. The Norwegian Radiation Protection Authority's detailed examination of hull sections recovered from compartment interfaces provided precise confirmation of explosive damage patterns that had been theorized during rescue coordination. Metallurgical analysis revealed explosive deformation characteristics consistent with internal pressure waves exceeding structural design limits by factors ranging from 300 to 500% of anticipated loading conditions. The hull fracture patterns demonstrated that compartmentalization doctrine had failed not due to design inadequacy, but because explosive forces had exceeded the physical assumptions embedded within structural engineering calculations by unprecedented margins. The pressure wave propagation analysis confirmed that explosive energy release had created structural loading conditions that invalidated fundamental assumptions about compartment isolation capability. Hull section examination revealed fracture characteristics indicating peak pressure levels that exceeded compartment boundary design specifications by margins that rendered isolation procedures physically impossible rather than procedurally inadequate. The evidence documented that compartmentalization failure resulted from explosive forces that exceeded engineering design assumptions rather than implementation failures of established emergency procedures. The recovered emergency communication equipment provided physical evidence of system behavior during the incident that corroborated crew member actions documented in written records left within the survivor compartment. Electronic component analysis revealed that emergency communication systems had functioned according to design specifications but remained unable to establish external communication due to antenna system destruction rather than equipment malfunction. The physical evidence confirmed that crew members had operated emergency systems correctly according to training protocols while being unable to achieve communication with rescue coordination due to infrastructure damage beyond their knowledge or control capability. Captain Lieutenant Dmitry Kolesnikov's written documentation recovered from Compartment 9 provided direct evidence of crew decision-making processes that demonstrated systematic adherence to emergency procedures under conditions that exceeded training scenario assumptions. The handwritten log documented crew member identification, time notation, and emergency status assessment that followed established protocols precisely, confirming that crew responses reflected appropriate application of training doctrine rather than panic or procedural deviation. The documentation timeline correlated directly with life support system performance data, confirming that crew survival periods had been limited by equipment capacity rather than procedural inadequacy. The physical evidence analysis revealed systematic patterns of institutional decision-making that had created barriers to rescue effectiveness despite availability of adequate technical resources for successful rescue operations. Documentation recovered from rescue coordination revealed institutional priorities that had emphasized operational security maintenance over international technical cooperation, creating systematic delays in rescue optimization that proved incompatible with crew survival timeline requirements. The evidence documented that rescue failure resulted from institutional coordination barriers rather than technical capability limitations of available rescue assets. The CIA intelligence assessment's institutional analysis, validated against subsequent Russian government documentation, revealed how operational security protocols had created systematic conflicts between information control requirements and emergency response coordination needs. Declassified communication records confirmed that international rescue capabilities had been available with technical specifications adequate for rescue operations, but institutional authorization procedures had prevented effective deployment within crew survival timeframes. The documentation pattern demonstrated that institutional priorities had systematically prevented rescue optimization that could have been achieved through international technical cooperation. The British Rescue System technical specifications, documented in Royal Navy operational records, confirmed that LR-5 rescue submersible capabilities had been compatible with rescue requirements created by the specific damage patterns, but deployment had been prevented by coordination protocol barriers rather than technical inadequacy. Equipment compatibility analysis revealed that British rescue systems possessed technical capabilities specifically designed for deep-water rescue scenarios with damaged submarine emergency interfaces, suggesting that successful rescue operations could potentially have been achieved through effective international coordination within appropriate timeframes. The Norwegian diving capability documentation revealed that offshore oil industry assets had possessed technical capabilities for emergency, hull access, and crew extraction that were specifically applicable to rescue requirements created by the damage patterns. Technical specification analysis confirmed that Norwegian diving systems had been designed for emergency scenarios involving structural damage, personnel extraction, and deep water operations that matched rescue requirements more closely than Russian naval rescue capabilities. The evidence suggested that effective rescue coordination could potentially have utilized Norwegian technical capabilities to complement Russian coordination authority and achieve successful crew extraction. The system design modifications implemented following forensic analysis addressed fundamental assumptions that had created systematic vulnerabilities identified through incident investigation. Russian submarine emergency systems underwent comprehensive redesign to eliminate information architecture limitations that had prevented accurate damage assessment during emergency conditions. Emergency communication systems were modified to provide redundant transmission capability independent of primary antenna infrastructure, addressing communication failures that had prevented coordination between trapped crew members and surface rescue assets. The International Rescue Coordination Framework modifications reflected institutional recognition that submarine rescue operations required information sharing and technical cooperation that conflicted with traditional operational security protocols. NATO submarine rescue cooperation agreements were established that provided predetermined authorization frameworks for international rescue coordination, eliminating institutional barriers that had prevented effective asset deployment during emergency conditions. The modifications recognized that submarine rescue effectiveness required international technical cooperation that could not be achieved through ad hoc coordination procedures during emergency conditions. The rescue equipment standardization initiatives addressed technical compatibility problems that had prevented effective coordination between different national rescue capabilities. International submarine rescue standards were developed that specified common interface requirements, communication protocols, and coordination procedures that enabled rapid integration of multiple rescue assets during emergency operations. The standardization recognized that effective submarine rescue required technical interoperability that could not be achieved through equipment adaptation during emergency conditions. The training doctrine modifications addressed cognitive patterns that had created systematic biases toward reactor-centric threat assessment rather than comprehensive emergency evaluation. Submarine crew training was redesigned to emphasize damage assessment capabilities that could function effectively under conditions where primary diagnostic systems had been eliminated by catastrophic damage. Training modifications recognized that emergency response effectiveness required adaptive problem-solving capabilities that could not be achieved through procedural compliance alone when actual emergency conditions exceeded training scenario assumptions. The emergency life support system redesign addressed resource consumption patterns that had proved inadequate for rescue coordination timeframes that exceeded original design assumptions. Emergency oxygen generation, carbon dioxide removal, and atmospheric purification capabilities were increased to provide survivability for extended rescue operations that might require international coordination and technical integration periods longer than originally anticipated. Life support modifications recognized that rescue operations required survival capability that exceeded original rescue coordination timeline assumptions. The communication system redundancy improvements addressed information pathway failures that had prevented coordination between compartmentalized crew groups and external rescue assets during emergency conditions. Emergency communication systems were redesigned to provide multiple independent transmission pathways that could function despite structural damage to primary communication infrastructure. Communication modifications recognized that emergency coordination required information pathway redundancy that could not be achieved through single-system designs vulnerable to catastrophic damage. The institutional decision making framework modifications addressed authorization hierarchy limitations that had created systematic delays in emergency response coordination when timeline constraints required rapid technical cooperation. Emergency authorization procedures were established that provided predetermined delegation authority for international rescue coordination, eliminating institutional barriers that had prevented effective resource deployment during time-critical emergency conditions. Authorization modifications recognized that emergency response effectiveness required decision-making authority distribution that could not be achieved through normal operational hierarchy procedures during crisis conditions. The long-term implications for submarine safety doctrine reflected recognition that effective emergency response required integration across design, procedural, and international coordination domains rather than improvements within individual system categories. Submarine safety philosophy was modified to emphasize diagnostic transparency and international rescue compatibility as primary design requirements rather than secondary considerations subordinate to operational security objectives. The doctrinal modifications recognized that submarine safety required fundamental integration of technical capability and institutional coordination that could not be achieved through isolated system improvements. The forensic evidence analysis revealed that the disaster had resulted from systematic incompatibilities between design assumptions, institutional procedures, and coordination requirements, rather than failures within individual technical or procedural domains. Physical evidence confirmed that technical systems had functioned according to design specifications while creating emergent vulnerabilities when combined under catastrophic stress conditions that exceeded individual system design assumptions. The evidence documented that effective submarine safety required systematic integration across technical, procedural, and institutional domains that recognized the limitations of isolated system optimization. The investigation conclusions emphasized that submarine rescue effectiveness required fundamental recognition of coordination complexity that exceeded traditional operational security frameworks and technical system design approaches. Successful rescue operations required information sharing, technical cooperation, and authorization procedures that conflicted with established operational security protocols, necessitating institutional modifications that integrated rescue effectiveness requirements into normal operational planning rather than treating rescue coordination as exceptional circumstances requiring ad hoc procedure development. The systemic lessons derived from forensic analysis emphasized that complex military system safety required design philosophy integration that recognized coordination requirements as primary design constraints rather than secondary operational considerations. Submarine safety doctrine was modified to emphasize that emergency response capability constituted a fundamental design requirement that required integration of technical capability, institutional procedures, and international coordination frameworks from initial design phases, rather than subsequent operational adaptation.